So let's do a thumbtack color thing. So let's do something similar where I give you guys a whole bunch of thumbtacks and you're broken into teams, so there are multiple samples. So down below is the number of thumbtacks that each given team found, orange thumbtacks that each given team found in the sample. So let's say we're counting orange thumbtacks for each sample. So yeah, down below we have the number of orange thumbtacks that the given team found in the sample. So that means, and then over here we have the number of teams that found the number of orange thumbtacks. So if we're looking at here, this means that 2 teams found 2 orange thumbtacks. And if we're looking here, that means 4 teams found 4 orange thumbtacks. And then here, 6 teams, 2 teams found 6 orange thumbtacks. So notice each team has their own statistic. So team 1, they found 2 thumbtacks, 2 orange thumbtacks, and so did team 2. And team 3 found 3 orange thumbtacks, and so did team 4. And so on and so forth. So each team has their own statistic. And then we took all those statistics and made a distribution. So this is a distribution of a whole bunch of statistics. So then we can then find the mean of all the samples. So rather than just having the mean for your own sample, you can find the mean for all the samples. So it's kind of a level above what we've been talking about, because previously we talked about just finding the mean for one sample. Now we're talking about the mean for a whole bunch of samples together. And we can find the mode, and we can find the median, and we can find the range for multiple samples rather than just one sample. So it was like we took all the samples and they had their own distributions, but then we made a distribution of all the samples. So some of the takeaways. So sampling error happens because remember we had a lot of variety here. It wasn't like every team was getting the same thing. So that means that when we sample, we don't always get exactly what we're wanting. And then the value of a statistic is going to vary from sample to sample. Therefore, for inferential purposes, the statistic cannot be assumed to accurately represent the population parameter. So even though our statistic, so let's take team 1. They found 2 orange thumbtacks. But the last team, they found 6 orange thumbtacks. So who's right and who's wrong? And maybe they're both wrong. So we can't always assume that our statistic accurately represents the population parameter, because when we take different samples, we come up with different results. So, but the central limit theorem helps out. So for the central limit theorem says that for any variable, no matter the shape or distribution in the population, when the sample is 30 or more above, then we know that the sampling distribution, which is the sample of all samples, will be normally distributed. And the mean of the sampling distribution is the mean of the population. So I'm going to say that again. The mean of the sampling distribution is the mean of the population if each sample has at least 30 or more people. It has to have 30 or more people in order for this to work. But if it has 30 or more people, sampling distribution mean is going to equal the population parameter. Okay, so sampling distribution, and also if there's at least 30 people in each sample, then the sampling distribution, which is the sample of samples, is going to be normally distributed. Even if originally each individual sample was not normally distributed, maybe each sample was originally skewed, but if there's at least 30 people in each sample, then the sampling distribution will be normally distributed. So, implication, when our sample is 30 or above, we don't have to draw all possible distributions because we know it will be normal. So sampling distributions are kind of a theoretical thing. We don't ever really take every single sample in most cases, but theoretically we know that if our sample has 30 or more people, then the sampling distribution will be normal. So let's look at this. So we have different types of distributions here. So let's say we have a normal distribution, and then these are the different sample sizes. So let's say the sample size was 3 for every single sample, but we took every possible sample, but the sample sizes had 3 people in each sample. So the normal, it remains normal, but it gets a little skinnier. Skewed, it's still kind of skewed, but things move more towards the center. And then uniform, it starts to look more normal. And then irregular, it starts to look more irregular, but it's still not quite regular or normal. But then as our sample sizes increase, all of these end up looking normal, even though they started out skewed or irregular or uniform. They all end up looking normal as the sample sizes get larger. These are sampling distributions we're looking at. So this is the distribution of all samples. So the mean of the mean. So this red line here marks the mean of the mean, because remember we have multiple means for every single sample in here. So each data point represents a different mean. So this person had a different mean than this person. But then we found the mean of all the means. So takeaway. We can be assured that the statistic of interest would be normally distributed across all possible unique samples of size 30 or more. So distributions, a normal distribution is really what we were after, which is why the central limit theorem is so important, because we're after that normal distribution in inferential statistics. With the normal distribution, we can then divide it into different pieces. We know that this line, half of everything is on this side, while the other half of everything is on this side. And 13.5% of the results fell right here, and 34% of the results fell right here. So we're able to divide it up into percentiles when we have a normal distribution. So let's say you got a 24 on the you scored 24 on the ACT. And this is the percentile. This is the population parameter. So this is the 74th percentile. We were able to figure out that a score of 24 is a 74th percentile because of the ability to divide a normal distribution into percentiles. So when we get different scores, we're then able to see where they fit on the distribution, because normal distributions are divided up certain ways. If we believe something is normally distributed in the population, we can make predictions about specific cases, percentiles, and the central limit theorem can make most things normally distributed.